Hello everyone, so this is a new video where I'm gonna show you the implicit and explicit time integration on two different examples. Quite frankly, I wanted to make a new video because the previous video was already getting long, but to be honestly, if I make a mistake, I can redo them in a more compact way. I don't have to re-render the entire almost 1 hour long video. So here it is. So let's look at one example. So if you remember our ordinary differential equation had two parts, right? So y dot of t equals f of t and y, and y of t0 equals y0. So in this case, we're gonna look at a function where, okay, I'm gonna change my y so they're a bit easier to, so y dot of t equals y of t minus t plus 2, and y of 0 equals 0. So this is my, so you can see clearly that, f, this is f here. I don't want to make it messy, so this part is f here, f of t and y. All right, so let's look, so y0 we know it's 0. Let's look at some values using explicit Euler. So in the explicit Euler, I'm just going to write it y1 is going to be equal to y0. Oh, I forgot, very important, delta t. Let's pick up 0.1. It's a relatively small. So y1 equals y0 plus delta t f of 0 and y0, right? So y0 is going to be 0, delta t is 0.1, and f of 0 y0 is going to be this part here. So it is y0, which is 0, minus t0, which is 0, times 2. So it's going to be 0.2. Y2 is going to be now y1 plus delta t f of 0.1 y1. So it's going to be 0.2 plus delta t 0.1 times f of 0.1 is going to be y1, which is 0.2 minus t 1, which is 0.1 plus 2 equals 0.2 plus 0.1 times 2.1. I hope I do it correctly. 0.2 plus 0.21 is going to be 0.42. Okay, so I'm just going to do it like you do on the homework. Let's do y3. So let's do it for y3. y3 equals y2 plus delta t f of t2 y2. Now we substitute. y2 is 0.42 plus 0.1 times, we have y2, which is 0.42 minus t2, which is 0.2 plus 2, 0.42 plus 0.1 times 2.22, 0.42 plus 0.222 is going to be 0.642. Okay. As I got the same result in training when I did them before, the live session, I have the same result. Let's keep the fingers crossed. Okay, so this is the explicit Euler, which is the easy part. Let's go now to the implicit Euler. All right, let's continue. I had some technical difficulties, but I fixed them. So now let's do the implicit Euler. So now we're going to do it a different color. Let's do it in red. So the implicit Euler, let's start with y1. y1 equals y0 plus delta t times f of t1 and y1. This is where things are interesting. So y0 is 0, delta t is 0.1 times, and now f of t1, y1. We have y1 here, we don't know what it is, so we have to put a variable, minus t1, which is 0.1, plus 2. So this is going to be equal to 0.1 y1 plus 0.19. Okay. So now this is an equation. Okay, in this case, of course, the equation is simple because I wanted to do it by hand, but in practice it's not. That's the whole point. But now I can turn this around. So I have 0.9 y1 equals 0.19, which means that y1 equals to, and I'm gonna use my son's high-tech calculator. He's 6 years old. So it's gonna be 0.19 divided by 0.9, 0.2111, and so on and so forth. So since I used now red, I'm gonna use blue to highlight the solution. All right, let's now go to y2. Did I do 3 here? Yeah, I did 3 here. y2 is going to be equal to y1 plus delta t f of t2 y2. So y1 is 0.2111 plus 0.1 times y2, we don't know, minus t2, which is 0.2, plus 2. So I can already move y2 on the other side. 0.9 y2 equals 0.2111 plus 0.18 equal 0.3911, which means that y2 is going to be equal to this divided by 0.9, 0.4346. Okay, I wish I could do it the third one in one row. Well, let's try to do it so we can have a neat. So y3 is going to be equal to y2 plus delta tf of t3 y3 is going to be equal to 0.4346. This is y2 plus 0.1 times y3 is y3 minus t3, which is 0.3, 0.3 plus 2 Okay. So now we can, let's do it in one go. Y 0.9, y3 is gonna be equals to let's try to do it directly. So it's gonna be 0.17 plus 0.4346 0.6046, which means y3 equals 2 9 0.6718. We do it like this. So let's go over. Okay. All right. So you see in these examples, which would be normally in the midterm and the final exam, it's not too bad actually. But I would like to give you an idea. So both, I mean, we have the explicit, we have the implicit. Let's have a look at the difference. So this is implicit. I'm going to write somewhere down implicit. This is implicit. And here we have explicit. So y1 is 0.2. Oh, I didn't want to do that, but I did by mistake. Anyway, so y1 is 0.2. y1 in the implicit is 0.211. So they're very, very close. I just want to delete this if possible. y2 is 0.42 in the explicit, and it's 0.43 in the implicit, and 0.642 in the explicit. y3 is 0.642 in the explicit, and 6.7. So here's the difference, it's a little bit bigger actually. But we still don't know which one is better or what's going on, and this is because we don't have the ground truth. But as it turns out, I have a surprise for you. So as it turns out, this actually, I took it from a real function, y of t equals e to the t plus t minus 1. And I can prove it to you. So I take the derivative now. Y prime of t equals e of t plus 1. Well, it doesn't really look like what I needed before. So let's do some tricks. So let's add and subtract the t minus 1. This is a trick you know from your high school math. So I add the t minus 1 and I subtract the t minus 1 plus 1. Now this is going to be equal to e to the t plus t minus 1, and this is going to be actually y of t, right? And then I have minus t plus 2. So this is going to be y of t minus t plus 2. It's exactly the equation there. I should have put the dot everywhere. Okay. And let's see if y of 0 equals 0. So y of 0, e to the 0 is 1, plus t 0 minus 1 equals 0, flushed. So this is the actual function that fits this differential equation. In fact, of course, I did not really solve the equation because most of the times you cannot solve it analytically. I actually worked backwards like I showed you here. So I picked some function, I took the derivative, and then I arrange it as a differential equation. But now the whole point of this is, let's see if we can actually in fact compute. So y of 0.1, and here I have to copy it because I actually don't have an exponential on my calculator, so I did it earlier. I hope I did it correctly. Okay, so now let's compare. So the true E of 0.1 is 0.205. Well, the y1 in the implicit method is 0.211, so it's a little bit overestimating it. And the explicit is 0.2, so it's a little bit underestimated, but if you see it's almost the same. They are both on both sides of the, one is underestimating, one is overestimating, but of about the same amount. Well, let's see y dot 0.2. Y dot 0.2 is going to be 0.421. Let's see. The implicit is 4.3. So from 4.21 to 4.3. So it's still pretty close, right? I mean, it's within 0.01. So 0.43. But actually y2 is 0.42, so the explicit one in this case actually works quite well. And this shows that in fact the explicit one, if the time step is small, if the function doesn't go wild, it behaves quite well. Let's look at the third one. The third one is y of 0.3, which is the true value 0.65. And here the implicit is 0.67, so it's getting a bit bigger, the difference. And here 642, so again the explicit one is close. And this is something not that surprising. You're gonna see it often. But still the implicit one, even though maybe the error is bigger, it's very, very stable. And the next example I will show is going to showcase the stability of the method. The second example I'm going to show you now, I'm not going to go with a differential equation. I'm going to pick a function directly. So I'm going to be the function y of t equals e of minus t. This is the function you saw before. Is this function here that you saw before? The blue function. Oh, this is the blue function you saw before. And so let's formulate it as a differential equation. So let's say that the starting point is 0. So y0, I'm going to do it in different color. So y0 is going to be 1, right? E to the 0 is 1. And if you take the derivative, y prime of t, actually minus e to the minus t is nothing else by minus y. So actually I'm going to just write e to the t equals minus y. So this is my differential, this is my differential equation, initial value problem. So let's look at the delta t equals 3. So this is a pretty gigantic thing. So before I apply the explicit Euler method here, I want to just do a generic step because I want to do some simplification because the derivative doesn't include t. So if I do the explicit step, yk plus 1 equals yk plus delta t times f of yk tk. This is going to be equal to yk plus, this is 3, times, and f is just minus yk, right? So this is going to be equal, so this is the equation we get is yk plus 1 equals minus 2 yk. I do this simplification so I can compute much faster y1, y2, y3 rather than, so y1 is going to be minus 2 y0 is going to be minus 2 y2. So again, this is for t1 equals 3, t2 equals 6, t3 equals 9 and t4 equals 12. I want to do it for all of them. So y2 is going to be minus 2y1, so it's going to be 4. y3 is going to be minus 8, and minus 8, and y4 is going to be 16. I hope I did it correctly. Minus 2, 4, minus 8, 16. Okay. It seems the same. All right, so let's now do the implicit version. I'm going to start the same way, doing the generic step to see if we can do any simplification. So yk plus 1 is going to be yk plus delta t times f of yk plus 1. I want to do different color, but I forgot now, so we leave it here. So yk plus 1 equals yk plus 3 times, and this is minus yk plus 1. So now I can move this term the other side, so I can have actually yk plus 1 equals yk divided by 4. So now I can do y2 is 1 over 4, this is again t2 equals, sorry, t1, not t2, t1 equals 1 over 4, t1 equals 3, t2 equals 6, y2 equals 1 over 16. I'm putting this aside. y3 is going to be 1 over 64, and t2 equals 9. Last one, t3 equals 12, and y4 equals 64 times 4, 256, 1 over 256, 0.00, let's say 4. Okay. I'm gonna just make some. Okay, 1 over 64 is 0.0156. Okay. Now let's compute the actual values. So I had to find a proper calculator to do the calculation. But anyway, I got the results. So y1 is 0.0498. Let's see how it compares. 0.0498. I don't know why I didn't put here not the fractions but the actual numbers. So this is 0.225. So y1 is 0.25 using the implicit method, and using the explicit method is 0.049. So it's quite, actually still the error is quite big, but it's nothing compared to the explicit. So this is the explicit. So the explicit is -2, so it's way off. So the second one, the implicit one, is 1 over 16, so 0.0625. So 0.0625, and here is 0.0025. So again, normally we would say it's a big difference, but still they are quite close compared to this one, which is now 4, so it oscillates on the other side. And anyway, I don't want to spend too much time here because you can see -2, 4, -8, 16. The explicit really oscillates, and the implicit kind of goes towards 0 in a steady way, similar to the real function. And I don't know if you remember, but this is the graph that showcases this very well. So the blue one is the real function, the red one is the implicit or backward Euler. But the time step is very big, but even with a huge time step, you see it sticks to the curve. It's a big error, but it doesn't start to behave very erratically. as it does the explicit Euler, which does the huge variation, positive, negative, which are quite a problem for stability of the system.